One of the challenges with this first part of the course is dealing with the idea of variable acceleration. Often for most of the course, you don't see that. We have a constant acceleration, something that occurs that is now, say, a constant acceleration of g, gravitational acceleration or something of that nature. And what I want to do today is look at non-constant acceleration and how those affect the equations that we use. And the goal here is that I've already gone through all of the derivations of this in the previous lecture, and this is a set of examples that cover this. So I'm going to start with something involving a motorcycle. The motorcyclist travels along a straight road at a speed of 27 meters per second. Brakes are applied. The motorcycle decelerates at a rate of minus 6t meters per second squared. So immediately I know that gravity or the acceleration is not constant. And I want to know the distance that the motorcycle travels before it stops. So the bike's going from left to right. And really, I just have to establish a coordinate system for this. And since the acceleration is given as a function of time, I want to integrate it once to calculate the velocity and again to calculate the position. I already know I can find velocity as a function of time and acceleration or position as a function of time. But I got to calculate it through. And I'm going to get different results than I will have if I had used a constant acceleration or deceleration. So integrate acceleration to determine velocity. So I have acceleration, which is equal to dv dt. And I know I can integrate that. And the only thing that I have to be careful about is setting up my acceleration terms. So I have acceleration dv dt, split it up into parts, dv equals va dt, and then I integrate from the initial velocity to the final velocity of interest and time, and start at 0 time. Now you can start usually, I could have been a little bit cleaner and just said t naught, but generally 0 to some t. If I'm wrong, it's t plus t naught. So it's not a t naught to t naught, t plus t naught would be the same result. Integrate it once, v minus v naught equals minus 3t squared, or v equals v naught minus 3t squared, which kind of makes sense. The motorcycle is decelerating with time. How long is it required for the motorcycle to stop? Starting with an initial velocity of 27 meters per second, I can do an I can calculate it down to 0. This is done in Excel. Not very difficult to do there. They're better packages, and I will sort of write them down. The one I'm recommending is either New Octave is great, and MATLAB, and in a separate video I talk about MathCAD and SMath desktop. But for graphing things, this is actually better. MATLAB, the only problem with it, of course, is you have to have a license. New Octave is freeware. So I get this done in 3 seconds. I calculate the distance traveled by going back to my fundamental definition, v equals ds dt, ds equals v dt. And remember, I probably should have mentioned at the beginning, this is one-dimensional motion. It's moving left to right. And so I don't have to worry about the vector terms so much. So integrating again, initial position, wherever it is, which could be a 0, to final position, 0 to t. And the distance traveled is s minus s naught. And then if I do the integral, it's minus t cubed plus v naught t plus a integration constant, but I don't need to include it because it disappears in the difference. S minus s naught is going to end up with a distance. I could either call that s minus 0 or delta s, and that's 54 meters. And here's another example. Particles traveling along a horizontal path with a velocity of 3t squared minus 6t meters per second. If it's initially located at the origin O, determine the distance traveled in 3.5 seconds and the particle's average velocity and speed during that time interval. So There, goes back, goes forward. Nice animation. And the velocity kind of looks like that. So it decreases, or it's negative and then positive. That's why it goes backwards and then forwards. And so between 2 seconds and 3.5 seconds, it's in the positive direction, moving to the right. Do the integral again. V equals ds dt. Do the integral of the terms. I get s equals t cubed minus 3t squared. I started here with s equal to 0 and time equals 0. And the other term, same thing, time equals 0, t. If I do that, super. Another example, so there's 2 more examples in this video. Person at A is hoisting a safe by walking to the right with a constant velocity VA equals 0.5 meters per second. Here's the person. What is the velocity and acceleration of the safe when it reaches the elevation at E? So it starts at 0 essentially. It starts somewhere down here and it ends up over here. Rope is 30 meters long and passes over the small pulley at point D. There you go. So 15 meters up, 10 meters to the point of interest. So I can sort of redraw this out as a schematic. 15 meters, C is distance y, C to D is 15 minus y. And the length dA here to here is going to be 15 squared plus x squared. And the length CD, which is the one I'm kind of interested in because that's the safe distance, is 15 minus y. So L equals LdA plus LCD. And if I do all the integrals and just start from the beginning, I have this integral for the hypotenuse. This is the side. And so y is going to equal 225 plus x squared minus 15, which works out really well for me. I didn't write it down, but here I have this distance that I got to worry about. This distance, that's the rate of change. And I want to calculate this distance, which is sort of the rate of change of this length. And dy dt can be written as dy dx dx dt. And so sort of like that. So this I got from the previous part of the problem. And so I can say after some manipulation, it's 1/2 2x over square root of 225 plus x squared dx dt. And dx dt is the rate of change, or the velocity of x, which is the person. So I can do the same thing for dy dt, and I can do all of the same sort of conversions, writing it in terms of dx dt. And I end up with an acceleration of 3.6 millimeters per second squared. Finally, this is one I do in lecture. And the reason I do it in lecture is that it's in personal lecture when I'm on a chalkboard. Variable acceleration, it's kind of a nice one because it covers everything. Brake consists of a piston attached to a barrel moving in a fixed cylinder filled with oil. Machine recoils with initial velocity v sub naught, piston moves, and oil is forced through orifices in the piston. So it's sort of, you're going to have motion like this. Causing the piston and cylinder to decelerate at a rate proportional to their velocity. So you're asked to find velocity as a function of time, position as a function of time, and velocity as a function of position. And you're given that acceleration is equal to minus kv. So this is kind of painful, this particular problem. So we can integrate a equals dv dt, and we got minus kv to find vt. We have vt, which equals dx dt to find xt. Super, no problem. This looks pretty good. And then we can say a equals v dv dx equals minus kv to find v sub x. So, all right, no problem. And just sort of a sense of what's happening, that's sort of the recoil motion of the piston. So for variable acceleration, we integrate A equals dv dt minus kv to find vt, okay? A equals dv dt, and it equals minus kv. So then I split the term up, dv over v, and this is where I realize I'm kind of stuck here, because now I have a ln. So I'm going to have ln from v0 to vt, ln vt over v0 by using sort of the subtraction relationship for lns. And this is from 0 to t, so it ends up being minus kt. So vt as a function becomes v0 equals minus kt, so it's decelerating and it's asymptotically approaching 0 with increasing time. On the next side, I want velocity as a function of time, and you can see that I'm already not so thrilled because I've got to deal with this exponential term, but v sub t equals dx dt, which is v0 e to the minus kt. So 0 to x dt dx equals v0 0 to t e to the minus kt dt. If I integrate these terms out, x of t equals v0 minus 1 over k e to the minus k 0 to t. So that's all there. That's just the integral. And so x of t is now a function of v0 over k 1 minus k e to the minus kt. So this is something that with increasing time, it's sort of approaching another asymptote, which is v0 over k, because e to the minus kt doesn't quite hit 0, but it kind of hits it close enough for engineering purposes. The last one, and the one I'd probably normally be kind of worried about, is a function of position, but hey, this works out really well because these two v's cancel. And so dv equals minus k dx, and integral v0 to v dv minus k dx. V minus v0 equals minus kx, and v equals v0 minus kx. So we have x as a function of time, v is a function of time, and x is a function of time, or v equals v0 minus kx. Okay, so we've written all of this in terms of the various terms. We've written this as all of the expressions. Sorry, and I should explain. V of t is equal to this. We can say e to the minus kt is equal to this relationship. And we can substitute this for the exponential term. Either way. But we still have the same result. All you did here was look at acceleration as a function of time, acceleration as a function of x. We also looked at velocity as a function of time generally, and a couple sort of cases where we looked at velocity as a function of x. This is not used as much as maybe some people might like, but it does give you here, it sort of emphasizes one point, which is the equations that you're using, you can derive any relationship you want to. We have a set of relationships we tend to use because we always assume constant acceleration. And to a large extent in this course, many of the problems do that. But it's still important to understand what the effect of these types of dampers are. And it gets more important when we eventually get to vibrations in chapter 22 in